Hello viewers, my name is Dr. Ajay, Associate Professor, Department of ECE, Institute of Aeronautical Engineering College, Hyderabad. Today's topic is definitions and terminology on VHF, UHF and microwave antennas 2. This topic is related to the course Antennas, Waves and Propagation. So let us start our session. So here the very high frequency, ultra high frequency, different antennas come under, operate under different frequencies. So there are some standard frequency ranges, these are known as radio frequency spectrum. The ranges are given as shown here. These are designation by the symbols of VLF, LF, MF, HF and VHF, and their frequencies are shown on the screen here. So the very low frequency range, it is the very low frequency range is 3 kHz to 30 kHz. The low frequency is 30 kHz to 300 kHz. The medium frequency is 300 kHz to 3 MHz. So high frequency is 3 MHz to 30 GHz. Now, in the previous session, we have discussed some VHF and UHF antennas, and in this session also we are going to discuss some of the very high frequency and ultra high frequency antennas, which are the microstrip antennas, the smart antenna, the lens antenna, the parabolic reflector antenna. So all these types of antennas come under the category of VHF and UHF antennas. Now here the basic definition of microstrip antenna. Let us discuss about the microstrip antenna. So why we are going for microstrip antenna? So the microstrip antennas are low profile antennas. So these are known as low profile, means less weight and low cost. The microstrip antennas are low profile antennas. So profile, the meaning of profile means it is less cost. So low cost and low weight, hence the name is given as low profile antennas. So a metal patch mounted at a ground level with a dielectric material in between constitutes a microstrip or patch antenna. These are very low size antennas having a very low radiation. So here a microstrip antenna basically consists of a ground plane here. And on the ground plane there is a substrate, and on the substrate there will be a patch attached over the substrate, and to this patch one transmission line is attached. So these are the basic features of a microstrip antenna here. So these microstrip antennas are useful because they can be printed directly onto a circuit board. So these microstrip antennas generally are used in aircrafts. But because these are very less weight and the size is also very less, and these can be fabricated by the process of photolithography onto the circuit board. So the microstrip antennas are becoming very widespread within the mobile phone market. Why? Because of these antennas are low profile, so less size and low cost. Hence, these are very famous in the mobile phone market. So these patch antennas are low cost, have a low profile, and are easily can be fabricated. So here a microstrip antenna for the fabrication over any surface, we use a technique known as photolithography technique. So the most common version of the printed antenna is the antenna which consists of a metallic patch upon a ground plane. So whenever we are going to design a patch antenna, so we need to take the ground plane and the substrate into consideration. On the substrate only patch can be placed. The shape and the size of the patch determine the frequency of operation of the antenna and its performance. So depending upon the shape and the frequency of operation, we can increase or decrease the bandwidth of the microstrip antenna. So here the photolithography. It is the process which use to transfer a pattern from a mask to a wafer. So in this photolithography process, we use the coating, developing and exposing of the patch here. The pattern is transferred into the wafer surface layer during a subsequent process. So generally, all these processes we use in the phenomenon of IC fabrication. So how we are going to fabricate the chip, integrated circuit board or integrated circuit chip. Similarly, we are going to design a patch by the process of photolithography, where we are going to subsequently follow different steps like coating, developing and exposing it. Printed antennas are inexpensive to fabricate using modern printed circuit technology. So these antennas can be easily mounted on the surface of aircrafts, spacecrafts, satellites, missiles, and even on handheld mobile devices. So generally, these antennas can be used in aircrafts, spaces, satellite, missiles because the weight of the antennas is very less. Hence, these are designed specifically for spacecraft, aircraft, and satellite communication purposes. There are three types of electromagnetic waves are radiated. The first part is radiated into the spaces. So generally, uh, this is the microchip antenna. So the microchip antenna, it is placed over the substrate here. This is the substrate, and this is the ground plane here. So this is the ground plane, and this is the substrate, and this is the patch. So there are three types of electromagnetic waves are radiated. The first part is radiated into space, which is useful radiation. So here, generally when we design a patch antenna, we give some input supply to the patch. Hence, the radiation is possible when we excite this microchip antenna. Here, some amount of radiation goes into the substrate here, downwards here, and some amount of radiation is escaped into the free space. And some amount of radiation goes into the ground plane here. Here there will be a ground plane here. So basically, a microchip array consists of a ground plane, a substrate, and also a transmission line. So whatever the electromagnetic energy that is radiated by the patch, some amount of radiation goes into the substrate, some amount of radiation goes into the ground plane, and some amount of radiation goes into the free space. So we need to increase the phenomenon of escaping the electromagnetic energy into free space from the patch. We call it as a fringing effect. So that is for a fringing effect. So whenever we design a patch antenna, so we need to observe that the fringing effect must be more. That means the amount of radiation that is happening into the free space must be more. So we need to design an antenna by changing the width and height of the substrate, or by changing we can control the bandwidth of the microchip antenna based upon some parameters. So that is the H parameter, that is the height of the substrate, or the thickness of the substrate, or width of the patch, So these height and width of the patch will control the radiation efficiency of the microchip antenna. So the three types of electromagnetics are radiated here. The first part is radiated into space, which is useful radiation. That means the fringing effect of the microchip antenna must be more here. The second part is diffracted, which are reflected back into space between the patch and the ground plane, contributing to the actual power transmission. The last part of the wave remains trapped in the dielectric substrate due to total internal reflection of the dielectric separation surface. The waves trapped in the substrate are generally undesirable. So here, some amount of radiation comes into the substrate here. Hence, these waves are trapped in the substrate generally undesirable. And also, some amount of radiation will be blocked or sandwiched between the patch and the ground plane. Right, so this is known as the actual power transmission. So the second part is diffracted waves, which are reflected back into space between the patch and the ground plane. And the first part is the radiated into space, which is known as useful radiation. So for effective radiation of the microchip antenna, the structure to be half wavelength resonator. So the length of the patch must be designed in such a way that L must be equal to lambda by 2. The wavelength must be half. So the length here, whenever design a patch here, this length must be lambda by 2 here. So the dielectric substrate should be sufficiently thicker and with a low constant. So the epsilon r value of the substrate must be very thick, and it must not be very increased. Why? Because the radiation efficiency stops if we increase the substrate value to very high value. So the height of the substrate should be limited to a fraction of wavelength. So there are different methods of microchip antenna: contacting feed and non-contacting feed here. And here in the contacting feed, the RF power is fed directly to the radiating patch using connecting elements such as microchip line and coaxial feed here. Non-contacting feed. So non-contacting feeds, we are going to excite the microchip antenna in an indirect method. So we are not going to give the signal RF power directly to the patch antenna or directly to the transmission line. So contacting feed means RF power is directly given by means of a wire to the microchip antenna. Non-contacting feed means it is a technique where RF power is not fed directly, to the patch antenna. So in a non-contacting scheme, the patch is not directly fed with RF power, but instead the power is transferred to the path from the feed line through the electromagnetic coupling. So the most commonly used non-contacting feed methods are aperture and proximity coupled feeding. So here we are having a center offset contacting feed. We are having center feed, offset feed, inset feed, and quarter wave line feed here. So here in the center feed antenna, what we are going to do is, if this is the patch here, we are going to give the excitation or input exactly at the center of the microchip antenna. Similarly for offset, what we are going to do is, we are going to give the signal either the corner ends, hence the name is given as offset feed. What is inset feed? So inset feed means we are going to inject the terminals of the transmission line inside the substrate of the patch. Inside the patch here, we are going to insert the transmission line inside the patch antenna. Hence the name is given as inset feed transmission line. And here the quarter wave feed line. So for quarter wave feed line, the transmission line is taken as lambda by 4 line. Lambda by 4 transmission line is given as input to the patch. The transmission line taken is designed as lambda by 4 line to the patch antenna. So center feed, offset feed, inset feed, and quarter wave line feed. These are the techniques where we are going to give the RF power directly to the patch antenna. So in non-contacting feed, we are going to use the aperture and proximity coupled feed systems. The next one is the smart antennas. Generally located with a base station, a smart antenna system combines an antenna array with a digital signal processing capability to transmit and receive in an adaptive, spatially sensitive manner. So in other words, such a system can automatically change the directionality of the radiation pattern in response to its signal environment. A smart antenna is nothing but it's an antenna where the bandwidth can be changed according to the requirement. So here, when more number of subscribers are there in one particular area, so automatically the smart antenna will direct all its radiated energy to that particular direction. So we are going to design a smart antenna so that it works automatically. It will change the directionality of its radiation pattern. Suppose the radiation pattern of the antenna is this, and if there are 2 subscribers here, if there are 4 subscribers here, then the radiation will be shifted directly to the where the subscribers are more. So where the mobile units are more, automatically the direction of the radiation pattern is changed according to the signal environment. Suppose if there are more than 100 subscribers in this direction, then automatically the radiation pattern is shifted in this direction. So here, smart antenna, it is nothing but it's a system designed with an antenna array and a DSP processor. So this DSP processor will decide to which direction the antenna elements must be automatically shifted. The phase shift of the antenna array depends upon the DSP. Suppose here there is a DSP unit here. On this DSP unit, we are going to attach 5 antenna elements here. So whenever a signal is coming here, this DSP will decide. The direction of arrival. That is the direction of estimation. From which direction the signal is coming. So based upon this, the DSP will direct all these antennas elements into this. It will establish a link towards the nearest base station. So wherever the subscribers are there, so automatically all its energy will be radiated in that direction based upon the direction of arrival estimation. So we call it as a DOA, direction of arrival estimation. So here the smart antenna is designed with a DSP processor and an antenna array which is capable of to transmit and receive an adaptive, spatially sensitive manner. Adaptive means accordingly to the signal environment dynamically. The DSP will take logical decisions and direct the electromagnetic energy to the intended direction. So what is an adaptive array? An array which automatically turn the maximum beam in the desired direction, so while turn the null in the undesired direction is known as adaptive array. So an array which automatically turn the maximum beam in the desired direction while turn the null in the undesired direction is called adaptive array. So here, suppose there are 4 antennas. These 4 antennas collectively we call it as an array. So here this is an array, basically a simple array. So here there are 5 subscribers here, and here there are 50 subscribers here. And this DSP processor will detect the direction of arrival estimation according to the signal environment. So wherever the DOA estimation is high, then automatically all these direction, there will be some phase shifter here. These are known as a phase shifter attached to each of the element of the array. The phase of the element of each of the array will be directed towards the 50 subscribers automatically. Hence the name is given adaptive array. So adaptive means it is going to make null in the undesired direction. So here this is the undesired direction. Why? Because there are no subscribers here. Here there are 0 subscribers, and here there are 0 subscribers, and here there are 0 subscribers. So automatically the radiation is shifted to where according to the requirement of the mobile units or mobile subscribers. The adaptive array adjusts itself in the desired direction with the awareness of its environment. So in modern adaptive arrays, the output of each element in the array is sampled, digitized, and then processed using computers. So in modern adaptive arrays, the output of each element in the array is sampled, digitized, and processed using computers. Such arrays are commonly called smart antennas. So here we are going to use 2 techniques for the smart antennas. One is the direction of arrival estimation. The other one is beam steering. So here, from which direction the signal is coming or reaching to the array, based upon the direction of arrival estimation, the beam of the array will be steered to the intended direction. So to whichever the direction we want to transmit the signal, so automatically the adaptive array will automatically transfer by the technique of beam steering. It directs the energy to the intended direction by what we call it as beam steering. The main purpose of standard antennas are to be effectively transmit and receive radio signals. So there are 2 additional functions which are direction of arrival estimation and beam steering. So in order for the smart antenna to be able to provide the required functionality and optimization of the transmission reception, so we need to detect the direction of arrival of the required incoming signal. So from which direction the signal is coming, the array will detect. So the information received by the antenna array is passed to the signal processor, that is the DSP processor within the antenna, and this provides the required analysis. So the DSP processor will perform all the analysis of what is required based upon the DOA. So based upon the antennas will detect the signal. The signal is passed to the DSP processor, and this DSP processor will take logical decisions and provide some mathematical analysis to which direction the beam has to be steered. So basic formation of a beam of energy from a set of phase arrays. So using phase antenna arrays, it is possible to control the shape and direction of the beam from multiple antennas based on the antenna spacing and phase of the signal from each antenna element in the array. So the creation of the beam using the technique of interfering and constructing the patterns, we call it as a beam forming. So the creation of beam using the technique of interfering and constructing patterns is called as a beam forming. The next definition is beam steering. So what is the beam steering? So with the direction of arrival of the required interfering signals analyzed, the control circuitry within the antenna is able to optimize the directional beam pattern of the adaptive antenna array to provide the required performance. So it is the way in which a beam pattern can be dynamically altered by changing the signal phase in real time without changing the antenna elements or other hardware. So it is the way the beam steering, it is the method where the beam pattern can be dynamically altered by changing the signal phase in real time without changing the antenna elements or other hardware. So just the phase of the phase shift of the phase shifter is attached to every of the element of the array. So the phase of the array will be changed automatically according to the signal environment here. So we need not add extra hardware or extra circuitry to the existing elements. So automatically the beam will be steered to the direction where the number of subscribers are more. Hence the name is given as smart. Hence the name is given as smart antenna. The two types of antennas are there: switched beam smart antennas and adaptive array smart antennas here. Switched beam smart antennas. So the switched beam smart or adaptive antennas are designed so that they have several fixed beam patterns. The control elements within the antenna can then select the most appropriate one for the conditions that have been directed. Although this approach does not provide complete flexibility, it simplifies the design and provides sufficient level of adaptivity for many applications. What are adaptive array smart antennas? So adaptive antenna arrays allow the beam to be continually steered to any direction to allow for the maximum signal to be received or nulling of any interference. So whenever the signal where there are no number of subscribers are zero, in that direction the energy is the electromagnetic energy is made null. That means the signal is made null here, and where the subscribers are more, the signal there will be some maximum signal is directed in the direction without any interference. So both types of antennas are able to provide the directivity, although decisions need to be made against cost, complexity, and the performance requirements regarding which type should be used. So switched beam means a finite number of fixed or predefined patterns or combining or strategies. So adaptive array means an infinite number of patterns. A finite number of fixed or predefined patterns or combined strategies. So adaptive array means an infinite number of patterns that are adjusted in real time. So in switched beam, so already there are some predefined patterns exist. Suppose there is a sector here. Let us assume this sector is divided into three. Suppose this is one sector, and this is another sector, and this is another sector. So there are three sectors. So let us assume this sector is 120 degrees. Each has 120 degrees here. And here, predefined patterns. That means, suppose there is a smart antenna here. There is a smart antenna here. So where the radiation is shifted here, the radiation is divided here like this. The radiation is divided into three sectors at different angles of 120, 120, and 120 out of 360 degrees. So these are the three fixed patterns given by the smart antenna. So here there are, suppose there are 10 subscribers, and these 10 subscribers will use only this radiation pattern. Suppose there are here 20 subscribers, these 20 subscribers will use only this radiation pattern. And here there are 40 subscribers, these 40 subscribers will use only this third radiation pattern. So this is 1, this is 2, and this is 3. So suppose if this in the first radiation pattern, if the number of users increase, the same amount of bandwidth that is allocated, that is predefined, it will be used though the number of users increase. So here even from 10 to 20, the users are increasing. The radiation pattern will not be shifted to this in this direction. So hence the name is given as a switched beam. A finite number of fixed predefined patterns or sectors are divided. So here there are three sectors. We have given three patterns, fixed patterns. So accordingly, these patterns are used irrespective of the number of subscribers. In adaptive array system, this is not the case in the case for the adaptive array system. Suppose in adaptive array system, automatically the number of users. Suppose there are two users are there here. It will be the radiation will be directed to this portion. Suppose if there are 10 users here, some amount of radiation is shared to this 10. If there are 100 users here, so maximum amount of signal is given to this direction. So like this, in real-time environment, the smart antenna will work based upon the requirement. So this is the switch beam or a predefined patterns. So instead of shaping the directional pattern with the metallic properties and physical design of single element, a switch beam system combines the outputs of multiple antennas in such a way as to form finally directional beams with more spatial sensitivity, selectivity that can be achieved with conventional single element here. Adaptive array antenna. So what are adaptive antennas? Adaptive antenna technology represents the most advanced smart antenna approach to date. Using a variety of new signal processing algorithms, the adaptive system takes advantage of its ability to effectively locate and track various types of signals to dynamically minimize interference and maximize intended signal reception. So both systems attempt to increase the gain according to the location of the user. So this is the DO estimation of all the signals. The next antenna is reflector antennas. Reflector antennas. So the antennas are designed to reflect the incident electromagnetic waves from separate source known as reflector antennas. So these reflector antennas also comes under the category of high frequency antennas. So the range is very high frequency. So these antennas belong to the category that offers high directionality while radiating. So a reflector antenna needs another antenna for radiation to happen. So a reflector is basically it's one type of antenna. We need to excite this reflector antenna. Suppose this is here there is a conductor here, a metal rod is there. We need to transmit the electromagnetic energy for this. So hence another antenna is used. That antenna we call it as, let us assume this as a horn antenna. So from horn antenna we are going to direct the energy towards the metallic rod, and from the rod the energy is radiated and reflected back here. So reflector antenna is a combination of feed element and the reflecting surface. So here reflector antenna, this is the reflecting antenna, and this is the surface of the reflecting rod here. So we are providing excitation here. Hence here this is known as the active element, and this is known as the passive element. So reflector antenna is a combination of feed element and reflecting surface. Is required to provide excitation to the reflecting element. This means it is composed of an active and a passive element. So the antenna that is used for provide excitation is known as the active element. So the basic definition of antenna active means which provides excitation. We call it as an active element here. While the one that radiates the energy emitted by the active element is the passive element, which is nothing but the reflecting surface. While the one that radiates the energy emitted by the active element is the passive element, which is nothing but the reflecting surface. So generally for a source antenna, where we are going to provide excitation, we use a dipole, horn or a slot antenna. The primary, the radiation pattern of the field is referred to as a primary pattern, and while the pattern that is reflected or originating from the reflector is referred to as a secondary pattern. So the radiation pattern of the field is referred as primary, and which is originating from the reflector is known as the secondary pattern here. So there are different types of rod reflector antenna. One is rod reflector. So here, as the name is indicated, the type of reflector possesses the shape of a rod here. So most of the amount of energy is being wasted from this rod reflector antenna. So whenever we are going to transmit energy from this rod, some amount of radiation falls on this, some amount of radiation goes backside of the rod reflector. So some amount of energy is wasted in the rod reflector antenna. The next one is a parabolic reflector antenna. So this type of reflector is designed in the structure of a parabola, employing the properties of a parabola, which is known as a parabolic reflector. So the active element is present focusing on the main axis. So there will be a focus on this is the focus of the parabola reflector. On the focal point, we are going to place a source antenna which is known as the horn antenna. From this horn antenna, all the energy is radiated towards the reflector antenna, and from the reflector, the energy is being reflected from the reflector to the intended direction. So here, this is the basic principle of the parabolic reflector antenna. So always, it is preferable that at the focal point, the active element is placed for exciting the parabolic reflector antenna. So the active element is present focusing on the main axis. This leads to the reflecting the radiated wave in the direction parallel to the main axis. So the frequency range is we can use as a frequency of in megahertz range, above 1 megahertz range. So the focal point inside the aperture, F by D ratio. So what is this F by D ratio? So the performance of the parabolic reflector antenna depends upon the F by D ratio. Suppose if we are going to place the focal, the feed point inside the focal point. Suppose this is the parabolic reflector antenna and this is the focal point. We are going to place the source element inside the focus here, inside the focus. So then what happens? It is difficult to provide the adequate uniform aperture to the source. An adequate uniform aperture. Why? Because all the electromagnetic rays will not reach the directorates at the same time interval. At the same time interval, all the reflected rays will not reach to the are not illuminated to the directrix at the same time interval. Hence, a uniform aperture to the source is not formed by means of this technique here. Focal point in the plane of aperture is placed. Highest gain is achieved by placing exactly on the focal point. That is the source element. The active element is placed exactly on the focal point, out of which the highest gain is possible. A uniform illumination, a plane wave is formed through this technique. And if we are going to place this is F focal point, we are going to place the source away from the focal point. Some amount of radiation is wasted. It goes beyond the parabolic reflector antenna. So some amount of electromagnetic energy is wasted. It is not going to touch the parabolic reflector antenna. It is going to the backside of the parabolic reflector antenna. So it is difficult for us to focus all the radiation from the source to the surface. Spillover. So this measures the amount of radiation from the feed element. So the non-captured rays, we call it as a spillover. The non-captured rays from the primary source antenna to the parabolic reflector antenna, we call it as a spillover. So we should design a parabolic reflector antenna in such a way that the spillover must be very less here. So due to the finite size of the reflector, some of the radiation from the feed antenna will travel away from the main axis at an angle greater than thus not being reflected. It means that sometimes if the design of the reflector is very less, suppose if the design of the reflector is very less, some amount of radiation is going to the backside. So this non-captured rays, these are known as non-captured rays, we call it as a spillover. So we need to design a parabolic reflector antenna in such a way that all the rays will be captured effectively by the parabolic reflector antenna. So this depends upon where we are going to place the active element, whether on the focal point or inside the focal point or outside the focal point. Back lobe radiation. So what is this back lobe radiation? So while listening, spillover noise pickup increases. So in addition to this, few radiations originated from primary radiators are absorbed in the forward direction. Such radiations get added with the desired parallel beam. So this is known as a back lobe radiation as it originates from the back lobe of the primary radiator. Suppose if this is the focal point here, suppose if there is any, if the device is not fixed properly, some radiations will be coming to the backside. Some radiations will be coming from the backside of the active element. And some radiation is going to fall on the parabolic reflector antenna, and these are reflected. And these are going to add with this, this reflected energy will add with this back radiations. Right? So hence, the field strength in the back lobe will be increased. Hence the name is given as back lobe radiation as it originates from the back lobe of the primary radiator. Cassegrain feed system and offset feed system. So here in Cassegrain feed system, we are going in basic parabolic reflector operation. These electromagnetic rays are directed and coming back in this direction. So this is known as some amount of rays is blocked by the horn antenna. Some amount of rays are going reflected here, like this. and some amount of rays are being blocked by the horn antenna. You can see here in the figure here. Suppose this reflector antenna, this is the primary source antenna. Amount of radiation is falling on the reflector and coming back here. It is going to fall on the reflector and coming back in this direction. That means it is this region of horn antenna is not this is known as the blocking region. Why? Because the electromagnetic rays reflected are being blocked by the horn antenna. Hence the name is given as a blocking system. This blocking can be overcome in the Cassegrain feed system. So in the Cassegrain feed system, exactly on the focal point, we are going to place. This is the vertex here. So on the vertex, we are going to place the horn antenna. The horn antenna is placed. The active element is placed on the vertex, and on the focal point, another subreflector, a small subreflector antenna is placed. So all the electromagnetic rays fall here, and they are going to reflect to the main reflector. This is the main reflector. This is the subreflector. This is the focal point. So 2 times the reflection is happening here. 2 times the reflection is happening in this technique here. So from this technique, there is no blocking here. So blocking can be overcome by the Cassegrain feed system. And in the offset feed system also, blocking can be overcome by changing the angle, of the active element. Suppose if we are designing antenna here, this is the focal point here. If we are going to change the direction, the angle of the primary antenna, all the radiations fall on this. This will be directed here. So no electromagnetic radiations are falling on the horn antenna. So here also blocking can be overcome here. Here also blocking can be overcome. So this is offset feed system. So this form of parabolic reflector antenna is offset from the center of the actual antenna dish used. Now the next one is lens antenna. These are antenna made up of glass where the converging and diverging properties of lens are followed here. So in the lens antenna, these are designed with a lens, hence refraction takes place here. So for this lens antenna also there will be one focal point. On this focal point only we are going to place the primary antenna. So from the primary antenna all the rays fall on the lens, refraction takes place, and parallel rays are produced after refraction from the lens. So the frequency of operation is about 3000 megahertz. So all the rays that are here, this is the lens antenna. This is the focal point here. So from this focal point, all the rays are diverged here. All the rays are sent in parallel to the plane wavefront. This phenomenon is known as divergence. So the rays that pass through the center of the lens are less refracted than the rays that pass through the edges of the lens. So all of the rays are sent in parallel to the plane wavefront. This phenomenon is known as divergence. And similarly, if this is the focal point, this is lens. So all the rays, the beam gets refracted and meets at a point here. The refraction takes place. They are going to meet at a point here. Hence the name is given as the convergence here. So all are going to converge at one point, at the focal point. The same procedure gets reversed if a light beam is sent from the right side to the left of the same lens. Then the beam gets refracted and meets at a point called focal point at a focal distance from the lens. So this phenomenon is known as a convergence. So delay lens antenna. So dielectric lens or H-plane metal lens, delay lens. Here the lens, that means the electromagnetic rays are collimated and delayed by the lens material. So here it depends upon the thickness of the lens material. So the thickness of this lens is more at the center of the lens. Hence the electromagnetic rays that pass through the lens are delayed by the lens material. Hence the name is given as a delay lens. So these lenses are manufactured by means of the polystyrene, or the material lucite and polyethylene is used for the manufacture of lens antenna. On lens antenna, the same operation is for lens antenna. The spherical wavefront is converted to plane wavefront. Here the outgoing wavefront is speeded up by the material of the lens. So you can see here the thickness is less here. The thickness is very less at the center. Hence the electromagnetic rays when pass on the when fall on this lens material, this type of lens material, the waves are speeded up by the material of the lens as the thickness is very less here. Zoning. So the weight of the lens, sometimes it is difficult for us to carry the lens antenna from one area to the other area, or for long distance communication. So when we are going to traveling, it is very hard for us to carry the lens. Why? Because the weight of the lens is very high. So in such cases, we are going to zone the lens. That means the weight of the lens is reduced by removing some sections of the lens, which is known as the zoning of the lens. So here there are two types of zoning: curved surface zoning and the plane surface zoning. So curved surface zoning has less weight, mechanically stronger, and power dissipation is less. In plane surface zoning, the bulkier, it is mechanically weaker, and power dissipation will be more here. Wagner's principle. So it says that the sum of field at a point behind a plane having a screen and the field at the same point when a complementary screen is substituted are equal to the field at the point when no screen is placed. So it says that the sum of field at a point behind a plane having a screen and the field at a point where complementary screen is substituted is equal to the field at the point where no screen is placed. So generally here this is the technique using the Wagner's principle for slot antenna. So here there is a screen here. This is the complementary screen of this screen, and here there is no screen. Suppose this is the electric field is E, and when there is a screen, the complementary is E2, and when no screen, the electric field is E. So we can write it as the electric field is equal to E1 plus E2. So the total electric field of the slot antenna by Wagner's principle can be written as the electric field with the screen and complementary screen. With the screen and the complementary screen, the summation gives rise to the total electric field strength of the slot antenna. So E3 is equal to E1 plus E2 is the Wagner's principle electric field strength. So slot antenna, type of antenna with an opening cut of certain dimensions in a metallic conductor which is excited using a two-way transmission line or coaxial cable is known as a slot antenna. So these antennas operate in a frequency range of 300 MHz to 30 GHz. So the excitation to the slot is provided at center or half of the center here. So the type of antenna where some portion of the antenna is cut and excited by means of two-way transmission line, we call it as a slot antenna. So for references of all these antennas, we can refer John D. Cross, Antennas of Wave Propagation by Bakshi, and also K.D. Prasad, Antennas, Waves and Propagations. For all these types of antennas, basic definitions and design, applications, advantages, disadvantages, we can refer these textbooks. That is John D. Cross, Antennas of Wave Propagation by Bakshi, and K.D. Prasad by Antennas, Waves and Propagation. Let us close the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.